Assalamu alaikum. This is our CS1005 final project, an item-level price co-movement network built using CPI data from Pakistan. The core question we try to answer is, which everyday consumer items tend to rise and fall in price together? And does that pattern hold consistently across different cities and different years? To answer that, we built a network graph where items are nodes and the connections between them represent how closely their prices move together. Let's walk through exactly how we did it. Project overview. The goal of this project basically was to model price similarity between consumer items using real government data, and our data set came from the Pakistan Bureau of Statistics, where 36 months of CPI data covering April 2023 to March 2026 and which spanned 51 consumer items across 17 Pakistani cities was compiled. The approach was to build a network where an edge between two items means their prices co-moved, rose and fell together across multiple cities in the same year. The tools we used were Python for all of the computation, Pandas for data handling, NetworkX for building and analyzing the graph, and Matplotlib for visualizations. The first step was getting the data into a workable format, which turned out to be more involved and challenging than expected. We downloaded 36 monthly CPI annexers from the PBS website. The last 6 were already in Excel format, but the previous 27 were PDFs, which we converted to Excel manually. Every file was renamed in the format year_month.xlsx and placed in a single folder. A Python script was then written to merge all 36 files into one unified table with 1,837 rows and 22 columns. For missing values, we used linear interpolation, filling gaps by averaging the month before and the month after. This preserved the price trend without distorting the data. One data quality issue worth noting was that 19 items in Sukhar had all zero price vectors throughout the dataset. This appears to be a recording issue on PBS's side, so those entries were excluded from the similarity computation. Now, computing price change vectors. Well, rather than working with new prices which vary widely between items and cities, we converted everything into price change vectors. For each item in each city in each year, we calculated a month-to-month change in price, and that gave us an 11 value vector, the change from month 1 to month 2, month 2 to 3, all the way to month 11 to 12. For example, wheat flour in Islamabad in year 1 produced a vector that looked like plus 85, minus 404, plus 363, and so on. That sequence is essentially the price movement fingerprint for that item in that city in that year. Across 51 items, 17 cities, and 3 years, this generated 2,601 vectors in total, saved as a CSV file with over 28,000 rows. The reason for using change vectors instead of raw prices is that it puts all items on a comparable scale. A kilogram of flour and a restaurant meal can now be compared meaningfully. Now, with price change vectors in hand, the next step was measuring how similar any two items' price movements were. We used cosine similarity for this. Cosine similarity measures the angle between two vectors. It does not care about magnitude, only direction. If two items rose and fell in the same months, their vectors point in the same direction, and cosine similarity is close to 1. If they moved independently, it's near 0. If they moved in opposite directions, it's -1. For every city and every year, we compared every possible pair of items. With 51 items, that's 1,275 unique pairs per city per year. Across 17 cities and 3 years, we computed approximately 48,489 similarity scores in total, all saved again in a file called cosine similarities.csv. These scores are now the raw material the network is built from. With tens of thousands of similarity scores computed, the next step was deciding which of those scores were strong enough to actually draw a connection between two items. We used two threshold parameters for this. The first is tau. The cosine similarity threshold. An edge between two items only gets created if the similarity score exceeds tau in at least one city. The second is k, the city count threshold. The edge only survives if the condition holds in at least k different cities. This filters out coincidental single city patterns and keeps only relationships that are geographically consistent. After testing different values, which we'll cover in the sensitivity analysis, we settled on tau equals 0.5 and k equals 3 as our default parameters. This gave us 3 separate yearly graphs, y1, y2, and y3, as you can see. Here are the key statistics for each of the three graphs. Year 1, April 2023 to March 2024, produced 368 edges with a density of 0.29 and just 2 connected components, a reasonably dense, well-connected network. Year 2 dropped significantly, April 2024 to March 2025, only 158 edges, density down to 0.12 and 7 components. The network fragmented. This appears to reflect the combination of economic stabilization after earlier inflation shocks and some data quality limitations in the PBS annexers for that period. Year 3, April 2025 to March 2026 showed the strongest network of all, 587 edges, density 0.46 and 5 components. This points to a new broad wave of price co-movement consistent with widespread inflation affecting multiple sectors at once. This pattern across the 3 years is connected, then fragmented, and then even more strongly connected. The basic graphs treat all edges the same. You either have a connection or you don't. But we can extract more information by assigning weights to those edges. We built 2 weighted versions of each graph. Weighting scheme 1, our main scheme, sets the edge weight equal to n, the number of cities where the 2 items co-moved. A heavier edge means the relationship isn't just strong in one place, it's geographically widespread. That's a national pattern and not a local coincidence. Weighting scheme 2 sets the edge weight equal to the average cosine similarity across all cities, capturing how strongly the items move together on average. Both schemes produced very similar centrality rankings, which confirms that our results are not an artifact of one particular weighting choice. Slide 9, the weighted graph visuals. Here are the weighted graph visualizations. The thickness of each line represents the weight of that edge, so thicker lines mean stronger, more widespread co-movement between 2 items. As you can see, the dense cluster at the center is the main connected component, dominated by food items. Items on that periphery are more independent. Their price movements don't consistently align with the broader market. Those graphs were generated using NetworkX Sprint layout algorithm, which automatically pulls more connected items towards the center. Once the network was built, we ran 3 centrality measures on every item in every early graph. Degree centrality counts how many other items this item is connected to. A high degree item moved in sync with many others simultaneously. Closeness centrality measures how centrally positioned an item is, and that can it reach the rest of the network in fewer steps. Betweenness centrality measures how often an item sits on the shortest path between 2 other items, essentially how much it bridges different parts of the network. 3 observations stood out. First, beef with bone was the only item to appear in the top 5 across multiple years, making it the most consistently central item in the dataset. Second, year 1 was dominated by restaurant items like cooked dal at hotel, which aligns with the peak of food service inflation in that period. And third, year 3 shows a much broader mix, food, clothing, and energy items all central together, consistent with a macro inflation wave hitting every sector. The degree centrality table, as you can see, looking at the top item by degree centrality in each year. In year 1, it was cooked dal at hotel with a score of 0.58. In year 2, beef with bones topped at the latest 0.30, a lower absolute score consistent with the weaker network that year. And in year 3, beef with bone again led, this time with 0.74, the highest degree centrality in the entire dataset. The consistent centrality of beef with bone is economically meaningful. Beef is a staple protein whose price is influenced by a wide range of upstream inputs, feed, costs, fuel transport, so it naturally tends to move in sync with many other items across the economy. Looking at how the network evolved year over the year reveals some interesting structural patterns. From year 1 to year 2, the network lost 311 edges and only gained 101, a net loss of over 200 connections. That explains the significant drop in density we saw earlier. From year 2 to year 3, the recovery was dramatic. Only 62 edges were lost, suggesting a new and distinct wave of co-movement that emerged in 25 and 26. Despite all this fluctuation at the edges, the core of the network stayed stable. The main cluster, the largest connected component, held at 50, then 45, then 47 nodes across the 3 years. The backbone is resilient even if you experience economic fluctuations. Now, that means that only 41 edges persisted across all 3 years. That means the vast majority of price relationships are transient. They emerge under specific economic conditions and dissolve when these conditions change. 2 items were persistently isolated. Telephone charges isolated in all 3 years, and sandals isolated in year 2 and 3. Telecom pricing in Pakistan is heavily regulated, which explains why it doesn't co-move with the general market. We also measured within category density how well items within the same product category connect to each other. Transport had a density of 1.0 in all 3 years, a perfect score. Every transport item was connected to every other transport item every single year. This makes complete economic sense. You see, fuel prices, fares, and transport costs are all driven by the same input, oil. Clothing showed high density in year 1 at 0.71, then dropped in years 2 and 3, suggesting clothing prices decoupled somewhat after the initial inflation period. Foods within category density rose from 0.7 in year 1 to 0.54 in year 3, showing that food prices became increasingly synchronized in the most recent year. The strongest cross-category link present in all 3 years was between clothing and food. This is a striking finding for two seemingly unrelated categories. It reflects how macroeconomic forces like energy prices and currency depreciation affect both simultaneously. The main cluster in all 3 years was 60 to 67% food items, but it always contained items from every category. Price movements you see is not a food story, it's a macroeconomic story. To validate our parameter choices, we ran a full sensitivity analysis testing what happens when we change tau and k independently, first varying tau while holding k fixed at 3 using year 1 as a test case. At tau equals 0.3, we got 672 edges and only one isolated node, a dense network but possibly too permissive. At our chosen value of tau equals 0.5, we get 368 edges, still just one isolated node connected and interpretable. At tau equals 0.7, edges drop to 122 and 6 nodes become isolated, and tau equals 0.9, the network essentially collapses with only 19 edges and 37 isolated nodes. The network is highly sensitive to tau. Small increases rapidly reduce connectivity. Tau equals 0.5 sits at the sweet spot, strict enough to filter out weak relationships but loose enough to preserve meaningful structure. These visuals show the effect of varying tau directly. At 0.3 it's a dense web, but by 0.9 it's nearly empty. Tau equals 0.5 thus gives you the clearest, most informative structure. Now varying k, the minimum number city, while holding tau equals fixed at 0.5 at k equals 1, we get 700 edges, including many that are driven by just a single city's data. At k equals 3, our chosen value 368 meaningful edges, and at k equals 5 it drops to 170. By equals 10, only 35 edges survive and the network again collapses. K equals 3 filters out every single city coincidences while preserving nationally consistent patterns. One additional insight is that at every high k value, especially k equals 8, the items that survive are the most central and are basic staples like powdered milk and pulse mash. These are the items whose core movement is truly nationwide and persistent across nearly every city in the dataset. Here is the visual comparison for varying k. Low k gives a crowded graph with many weak edges. High k strips it down to only the most universally agreed upon relationships, while k equals 3 gives us a readable, meaningful network. Finally, we compare the two weighting schemes to make sure centrality rankings weren't sensitive to that choice either. Looking at the top 5 items where various centrality in year 1, both W1 and W2 agree on the number 1 item. Powder milk NIDO, Cult Smash and Gent Sandal swap positions between the two schemes, but both appear in the top 5 either way. The remaining spots were occupied by cooked dal and either sugar refined rice basmati, depending on the scheme. The rankings you see are highly consistent. This confirmed that the centrality findings reflect a genuine structure in the data, not a consequence and a consecutiveness of how edges are varied. Visually comparing W1 and W2 side by side, the overall structure is preserved across both the same dense core, the same peripheral items. The two schemes are essentially telling the same story. To summarize everything, here are the key findings from this project. Year 3 covering 2025 to 2026 shows the strongest price core movement in the dataset, pointing to broad inflation affecting all sectors of the economy simultaneously. Year 2 was the weakest year, likely a combination of economic stabilization and data quality limitations. Food items, form the backbone of the network in all 3 years, consistently making up 60 to 67% of the main cluster, and transport items were perfectly correlated every year. Clothing and food were the strongest cross-category link. This is evidence that macroeconomic forces, energy costs, currency depreciation, and monetary policy are the dominant driver of price movement, not sector-specific factors. Beef with bone is the only item that was consistently central across multiple years. Most of the relationships are essentially transient, and our default parameters, K3 and tau 0.5, are validated as robust by the sensitivity analysis. Both weighting schemes are giving consistent results, making the overall findings reliable. The broader conclusion is that Pakistan's CPI data, when modeled as a network, reveals the price inflation is systemic. When prices move, they move together across items, across cities, and across categories, driven by the same underlying macroeconomic forces. That's our project. Thanks for watching. This was the CS1005 final project by roll numbers 2551016, 2550826, and 2551011.